All right, so the first thing we got is just a simple application of Gauss's method. So the first thing that I'm going to do is I'm actually going to turn this into matrix form. We want to look at just the coefficients and then what the right-hand side is equal to. So the coefficients are 1, 1, 1, and then on the right-hand side of that row I have 5. I got 1, negative 1, 0. Don't forget the 0 for the z is equal to 0, and then we have 0 for x here, 1 for y, and then 2 for z is equal to 7. Now, to do Gauss's method, I'm going to start off by doing negative 1, row 1, that looks like this. And I'm going to add it to the second row. And the first row that I multiplied by negative 1 stays the same. Adding it to the second row, 1, negative 1, give me 0. That's what I wanted. Negative 2, and then negative 1. If I do this right, let's see what's going on here. Yep. And then negative 1 right here, and then negative 5, 0 plus negative 5. And then I leave the third row the same. And then what I'm going to do is I'm actually going to do I'm going to do 2 times the third row and then add it to the second row and then do a row swap from this one. So 2 times the third row, that's going to give me 0, 2, 4, 14. And I'm going to add that to the second row to get 1, 1, 1, 5. That stays the same. And then 0, 0, 3, 9. And then 0, 1, 2, 7. And with this, I can solve the whole system pretty much. If we want to get it in echelon form, we just do the row swap at the end just to make it clear that I have it in echelon form. 0, 1, 2, 0, 0, 3, 9, and then this was a 7. And we should see that from this bottom row that z is forced to be 3. And then if z is 3, you back substitute. So z is 3, so then 3 times 2 is 6. That forces y to being 1. And then x must also be 1, right? Because then this is 1 plus 3 is 4, and then x is 1. And the solution, the unique solution to the system is 1. X is 1, y is 1, and z is 3. Now, to this question, I want to do something similar. Let's just read it. For which values of k are there no solutions, many solutions, or a unique solution to the system? Now, we know that many solutions actually just means infinite solutions, but at this point in the text, they don't have that result, so they're saying many solutions. But that's fine. Let's answer this question regardless. So we want to see for what values of k we have no solutions, many solutions, or a unique solution. So I'm just going to make this into a matrix again. And I'm going to say, well, how do I do Gaussian reduction here? I'm going to do negative 3 the first row and add it to the second row. So negative 3 the first row and adding it to the second row, I get 0. And then negative 3 makes this a positive 3. Adding it, I get 0 again. And then it's k minus 3 because it's negative 3 here. And then I get this right here, right? So what can we conclude at this point? Well, we can see that if, right, k equals 3, then we're going to get 0 on the right-hand side over here, and then we get this equation, which is x minus y is equal to 1 as the only relevant equation, which is infinite solutions. And we can state then if k equals 3, then infinite solutions. And now the other thing that we could say is if k does not equal 3, we should see that we get a contradiction in these bottom equations, because here on the left-hand side we have 0. And if k doesn't equal 3, then that means that we have something not equal to 0, right? If k does not equal 3. And then you get that contradiction. So if k doesn't equal 3, then we get no solutions. And interestingly, we should then conclude something even further. K is either 3 or not 3. So then that means that the case where there's a unique solution cannot occur, and there's no k values, and no k values for a unique solution.